Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, my dear students. Today we are talking about the second part, part two of projectile motion. Now, in the first part, remember we talked about how projectile motion is objects that are launched or released. And with projectile motion, there's no forces acting on it beyond the force of gravity. And we assume that gravity is 9.81 meters per second acting downwards. We also assume that there's no air resistance, and we also assume that the speed or the velocity in the horizontal direction is always going to be constant, which means there's no external forces acting on it. Okay, so the velocity is constant in horizontal direction. In the vertical direction, however, it's not constant. It is constantly accelerating because of gravity. So let's talk about part two. Inshallah, you're going to find this just as easy. Let's have a look. So basically here we have some formulas that tell us about the position of the object in the x and the y direction. We also have some equations that tell us about the velocity, as-sur'a, for the object in the x and the y directions. Okay? And what you notice immediately is that those equations are very similar to those ones. Okay? Now those are the ones we used when we were talking about projectile motions that are launched from a horizontal line or dropped. Okay? Now, except this time, we're not talking about launched or dropped. We're talking about launched at an angle. Okay, so launched at an angle, which is something you will encounter if you're talking about cannonballs, for example, or kicking a football, or even launching a rocket. Okay, so, or a tank shell, or, there's many examples where objects are being launched at an angle. So what's the difference then? Well, the formulas are very similar, except now we've got cos and sine and all sorts of funny things. What's going on? What's going on is that we need the initial velocity. The formula is exactly the same, in fact. So you see this here, Vxi times t. Well, this is the new Vxi component. How come? Well, because remember we have an angle, and if we are going to calculate, this is Vxi, okay, and this is Vyi. So if I'm using SOHCAHTOA, right? So if I'm using the rule of triangles and angles, if I want to work out the speed in the horizontal direction, I have to take the initial speed, which is the hypotenuse, multiplied by, okay, if it's adjacent, by cos theta or cos theta, and then if it's over here on that side, okay, then it's going to be the opposite, which is going to be the hypotenuse, which is Vi, multiplied by the sine of theta. Okay, so if I'm trying to work out this side here, let me just show you an example. Then it's going to be the hypotenuse, Vi, multiplied by SOH, opposite over hypotenuse, sine theta. That's the formula. So it's exactly the same. That's going to be Vyi. It's going to be the hypotenuse multiplied by V sine theta. And that's what we did here. So if you notice over here, we replaced Vyi by Vi sine theta. Okay, that's all it is. That's all it is. So once you know this triangle, once you're familiar with it, you'll understand where this has come from, and where this has come from, where this has come from, and where this has come from. That's exactly the same process. It's just that now it is an angle, so we have to work out the x and the y components using the hypotenuse. Okay, so let's go ahead and look at a problem. Here we have a golfer who sends a ball over 3 meters high, a 3-meter high tree that is 14 meters away. So the first thing I want you to do is picture the problem. Here it is. So there it is. It is at 14 meters. It is 14 meters away. And the tree itself is about 3 meters tall. So the tree itself is 3 meters tall, from root all the way to the tip. طيب. The ball lands on the green, of course. So the ball goes from the green all the way to the green, and it's on a flat surface, okay, at the same level at which it was struck after traveling a horizontal distance of 17.8 meters. So basically the whole distance here, the horizontal distance from when it was launched to it landed, is 17.8 meters. Okay, if the ball left the club Okay, the club is the thing you use to hit the ball. If the ball lifted the club at 54 degrees above the horizontal and landed on the green 2.24 seconds later, okay, so the time is 2.24 seconds. Now we got to figure it out. What was the initial speed? And B, how high was the ball at that time? When it just went above the tree. So over here, how high was the ball? How high was the ball over here? And what was the initial velocity of the ball? So the easiest part is working out the initial velocity. Okay, let's see, if the ball lifts the club at 54 above the horizontal, what was the initial speed? Okay, so we have the formula, right? So we know that the final, x final, here we go. We're going to use this formula here. The final position equals the initial position plus velocity, the initial velocity, multiplied by cos theta. And طبعا, when we're talking about initial velocity, we're not talking about Vix, okay? Because this whole thing is Vix. We are talking about Vi, which is the hypotenuse, multiplied by cos theta, multiplied by time. Okay, so do we have any of this? Yes, we have a lot of it. We have the final position, which is 17.8. Do we have the initial position? 0 in the x-axis. Do we have the initial speed? Did they tell us the initial speed? No, that's what we're trying to work out. That's what we're trying to work out. So that's what we're trying to work out. Multiplied by cos 54, that's the angle they told us about, multiplied by the time, which is 2.24 seconds. Okay, great. So what do we do now? What do we do now? That's part A, of course. What we do now is we try and isolate VI and put it on one side of the equation. So how do we get rid of this? We divide by cos 54 times 2.24. So let's do that. Divided by cos 54 times 2.24. And then suddenly we can get rid of this, but of course we have to do it on this side as well. Cos 54 multiplied by 2.24. What do we have now? So now we have VI يساوي, that means equals 17.8 divided by cos 54 multiplied by 2.24 seconds, and that is this 17.8 divided by the answer, and we have 13.5 meters. Okay, so that is 1.32, which equals 13.5 meters per second. And that is the initial velocity. That is this velocity here. V يساوي 13.5 meters per second. Okay? And that's how you work V. Now, the next question says, the ball passes directly above the tree at 1.76 seconds. How high was the ball at that time? Now, you'll be tempted to say that it was 3 meters high, maybe, because the tree is 3 meters tall, but it passed above the tree. So we need to find the y position of the ball, the y position of the ball. I'm just going to make some space over here by getting rid of this stuff. Okay. And let's see, where's the y formula? The y position formula is y final, which is the final position of y, equals y initial plus vi, which is initial velocity, which we've just worked out, 13.5 meters per second, multiplied by sine theta, which is 54, multiplied by the time. And what is the time? 1.76 seconds. They were very nice to give us the time. And minus half times gt squared times 9.81 times 1.76 squared. So do we have the final position and the initial position? So we're looking for the final position, so we don't have that. That's what we're looking for. The initial position we do have. What was the initial position in the y? It was 0. So in fact, the initial position in the x-axis and the y-axis were both 0. So that we can replace with 0. And we have everything else. Do we have VI? We've just worked out VI, alhamdulillah, so 13.5. So all we need to do is plug it into the calculator really, and that will give us the final position. Before I even work it out, I should be able to get something above 3. Now, 3 is how tall the tree is. So I expect it to be taller than 3 meters. But hopefully it's going to be not so much taller than 3 meters. My prediction is it's going to be, see, the highest point is about 6, so it should be between 3.5 and 4.5. Yeah, I would say between 3.5 and 4.5. Let's see. Let's work it out. 13.5 multiplied by sine 54 multiplied by 1.76, okay, minus 0.5 times 9.81 times 1.76 squared, and the answer is 4. Y final equals 4.03 meters, which is what we expected. It is within the scope of what we expected. Always a good idea to have a sort of a rough approximation of what the answer should be. Okay, very good. Let's move on. Oopsie, what did I do? Okay, maybe hopefully just going to the next slide fixes everything. Yay, it did. Okay, and are things still there? Okay. Next slide. We've got follow-up questions. Follow-up questions. Okay, what are we looking at here? We are looking at what is the speed of the golf ball in the guided example 4.12 when it passes over the tree. So now they're getting a bit greedy. They want the speed of the golf ball when it passes over the tree. So that means they want the speed down here. What is the speed? Well, and you could be tempted to say it's going to be exactly the same, 13.5, but no, it's not. Speed remains constant in the horizontal axis, but it doesn't remain constant in the vertical axis. And because this speed is a component of both horizontal and vertical components, it's going to be different. So let's work it out anyway. So we need to work out the y component of velocity and the x component of velocity. So we're going to need both of these equations over here. Those will be very helpful. So let's have a look. So we have 40. Question 40. We need to work out the vertical component of velocity, which is Vx final ysawi Vi cos theta. Okay, and we need to also work out the y component, which is Vy final equals Vi sine theta minus gt, which is acceleration towards gravity times time. Okay, so let's have a look. With Vx final, we already know that Vi cos theta is going to equal, hang on, Vi is 13.5, which is just the initial speed. We already know that, we've worked it out. So Vx final is 13.5 multiplied by cos 54. And Vy final is 13.5 meters per second multiplied by sine 54 minus 9.81 multiplied by, what was the time which the ball passed over the tree? It was 1.76 seconds. Multiplied by 1.76, running out of space over here. Okay, so now it's just a matter of calculations really, and I would love to change the color of my marker. So VXF Isawi, VYF Isawi. We're not done just yet, so I'll tell you why in a minute. 0.5. Always be sure to understand what the question's asking for. So here we have 7.94 meters per second, which is great, kind of expected. That is the speed in the horizontal component. Now, the ball has a horizontal component and a vertical component. The vertical component is going to be VYF, but you see it's pointing down. So the first thing I expect is that it's going to have a negative sign as well. If it doesn't have a negative sign, we did something wrong. Times sine 54 minus 9.81 times 1.76. And that gives us negative 6.34 meters per second. Are we done? No, we're not done, because the question asks for the speed when it passes over the tree. It doesn't say the horizontal speed or the vertical speed. It says the speed. So it wants They want this. They want this. But we know how to work this out. We just take Vxf and we take Vyf and we square them and we find the square root. So in this case, V is going to equal the square root of this 7.94 squared plus negative, I like putting negatives in brackets. It's just good practice because with calculators, especially if using an old calculator like my calculator, it just gets a bit confusing for the calculator. So that's why it's better just to put it in brackets. Okay, so once we do that, we've got 40.24 plus what should be about 62 or 63, 7.94 squared, and the square root of all of that, and we get final velocity is 10. Oopsie daisy, sorry. Oh, you gonna work? Oh, come on. Yep, here we go. Sorry about that. 10.16, or actually, we're just gonna say 10.2. 10.2 meters per second. Okay, and that's the answer. That's the answer to number 40. Okay, so it's 10.2 meters per second. That is the velocity of the ball as it's passing over the tree. Very good. Let's look at question 41. This is the part I hate, rubbing all of this off. Okay, just bear with me. So question 41 says a soccer ball, football, is being, what's happening to it? It's being kicked. And that's another classic projectile motion question. So it's being kicked from the ground, okay, with a speed of 12 meters per second. 12 meters per second, which is not unusual. Okay, so let's have a look. I'm going to picture the problem. 41. So a ball is being kicked from the ground, and it is the initial angle is, does it give us the initial angle? 32 degrees, and the speed is 12 meters per second. That is excellent. What are the x and y components of the ball 0.5 seconds after it's being kicked? Come on, guys. Super easy stuff here. Super easy stuff. We're given the velocity. So once again, the equations are Vx final Yisawi Vi times cos theta. That's the x component, which is going to equal 12 times cos 32. Really, it's just plugging in stuff. Cos 32 times 12, and that is the x component. The final velocity after 0.5 seconds of being kicked is Vxf is equal to 10.18 meters per second in the x component, so that's Vxf. Now, does Vxf change? No. Remember, in the horizontal component, the velocity in the x-axis doesn't change. So that's why there's no time actually. So now let's have a look at the y component. Now the y component, we expect there will be time because the velocity does change with time. So it's going to be Vyf Yisawi Vi cos theta. Oh, sorry, not cos theta. It's going to be sine theta because we're talking about opposite. Sine theta minus gt, which is going to equal 12, and that's the initial velocity, sine 32, that's the angle, minus 9.81 multiplied by 0.5. Now that's where time comes in. And that's going to equal, once again, if it's going upwards, it's going to be positive. If it's going downwards, it's going to be negative. I expect it to be positive. Let's have a look. 12 times sine 32 minus 9.81 times 0.5, and that equals 1 point, let's have a look, 1.9, so it's nearly 10. What did I do here? Oopsie. I just worked out velocities instead of, I worked out velocities, didn't I? Meters per second. It's very important to read the question. It's very important to read the question. See the position, it's asking for positions, not velocities. Positions. Okay, very good. This is why we do this. Okay, so even teachers can make mistakes. The question's asking for position, not velocity. So we've just worked out the velocity in the x and the y component. Okay, let's work out the position instead. So get rid of all of this. I'm going to leave it in there. I could edit it out, but I'm going to leave it in there because hopefully this is a learning experience for you guys, that it's important to read the question properly so that you don't start working and then making a mistake. Okay, let's have a look. So 41, the soccer ball is kicked at 12 meters per second and 32 degrees. And let's have a look. So you want the final position in the x-axis, which is going to be xf equals x initial plus vi cos theta multiplied by time. Okay. Okay, of course, now we're talking about position, so position does change with time, but velocity doesn't, so that's why velocity didn't have a time in the x component, but position does have a time in the y component. And that's going to equal 0 plus 12 multiplied by cos 32 multiplied by 0.5, and that will give us 5 point. Let me just check the answer. 32 equals, yes, multiplied by 5.1 meters. That's the final position in the x. The final position in the y is going to be y final. And that's going to be y initial plus vi sine theta times t minus half gt squared. Y initial is 0, vi is 12, sine 32 once again, multiplied by 0.5 minus half times 9.81 times 0.5 squared, which is 0.25. 12 times sine 32 times 0.5, and that equals 3.17 minus 2 times 0.5 times 1.81 times 0.5, which is approximately 2 meters. Okay, that's how you do that one. Make sure you read the question. Please make sure you read the question so that you know it's asking for position or velocity. Okay, so that's that. Okay, let's look at question 42. Referring to problem 41, what is the x and y component for a soccer's velocity 0.5 seconds after it was kicked? We did work it out. So we've just worked it out. We worked it out the other way around. So please, if you're not sure, go back and watch the video. But basically, we've worked it out. Yeah. Okay. So just using the velocity equations instead of the position equations. Okay, back to the conceptual questions. Let's have a look. So in this question here, we have an example. You throw a ball to a friend with an initial velocity of 10 meters per second. So the first thing we notice is that, initial speed of 10 meters per second. So that is not the horizontal speed, not the vertical speed, that's just the initial speed, which is a component of both. Your friend catches the ball at speed t at the same level from which you threw it. So I threw the ball, here's the ball, I threw the ball, and my friend catches it at the same level. So his hands were out here, and that's a very amazing drawing, mashallah, Mr. Hussein, amazing drawing. And let's have a look at, here we go, and that's how I threw the ball. So I threw the ball at him and he caught the ball. What's the question asking? Make sure you read the question. Referring to the figures below, which of the plots 1, 2, or 3 best represents the speed of the ball as a function of time? So what's going to happen to the speed of the ball with time? And remember, we're not talking about the horizontal speed because the horizontal speed doesn't change. So it's going to be a straight line. The vertical speed does change. It goes positive, 0, and then negative. Why does it go to 0? At the highest point, the vertical speed is 0. Not the speed, the vertical component of the speed is 0. So let's have a look. That's wrong, because the speed is not 0. At the halfway point, the speed of the ball is not 0. It's the vertical component of the speed is 0. That's wrong. So plot 3 is already wrong. What about plot 1? Plot 1, it says the speed, halfway point, the speed is 15. So it speeds up at the halfway point, while number 2 says the speed slows down at the halfway point. Now let's just talk about common sense here. Is it going to speed up at the halfway point, or is it going to slow down? Now remember, if I drop this up, okay, and I can use this as an extreme example, rather than throwing in a parabola, I'm throwing this up. At the highest point, it's going to be 0. So basically, at the highest point, as the ball gets higher and higher, the y component gets smaller. Now, if the y component gets smaller and the horizontal component, the x component, stays the same, then it's going to be an overall speed that's less. Why? Once again, the x component stays the same, but the y component gets smaller. So therefore, the velocity, which is made of the y component and the x component, is going to be smaller. So in fact, it's going to be 2. So which are the plots? It's going to be plot 2. Okay, moving on. Range is affected by launch angle. Range is affected by launch angle. Taban. When you kick a ball, if you're playing football, if you kick a ball like straight on the ground, then the range of it is going to be a lot less than if you kick it high up in the air. And if you kick it really high up in the air, then it's going to spend a long time in the air, but it's not going to go a huge range. Now, oh, sorry. Let me go back. What do we mean by range? We mean the x distance, or the distance in the x-axis. That's range. So if I kick a ball straight up, it's going to spend a lot of time in the air, a long time, but it's not going to travel a lot. What if I kick the ball, I'm going to use a different color now, green. What if I kick the ball straight down? If I kick the ball straight down, what's going to happen to it? Once again, it's going to not spend a lot of, it's going to travel a bit of a distance, but it's not going to spend a lot of time. So then what if I kick it at an angle? So if I kick it at an angle, what's going to happen is it's going to experience that beautiful parabola, and it's going to travel a big distance. Now, depending on the angle, it's going to travel further or closer. And turns out the best angle to kick the ball or launch a projectile to travel the longest distance is going to be 45 degrees. Why is that? Well, it'll show you on the next page. Look. If I launch it at 60, it's going to spend more time in the air, as you can see. At 60 degrees, it's going to spend more time in the air, but it's going to land closer. If I launch it at 30 degrees, it's going to spend less time in the air, and it'll also land closer. If I launch it at 45 degrees, that's actually the ideal projectile for the biggest range, and that's going to travel the furthest. So immediately now you should always remember, how am I going to make a projectile go as far as I want it to? Launch it at 45 degrees, please. Okay, so here is a class worksheet that I've given you the other day. I'm going to go through the answers for those of you that haven't had a chance to do this with us. So we're going to go through the answers. The initial velocity of the ball at a horizontal component equals 5 meters per second. So here we don't have any angles at the moment. So we have a ball that's being launched. It has a horizontal component of 5 meters per second, and that is the speed in the horizontal component, or x-axis, and a vertical component equal to 6 meters per second. 6 meters per second. Interesting. At what point? What is the highest point of the result? What is at the highest point? Okay, so it does have. So it was launched at an angle by the looks of things. So it was launched at an angle, 6 meters per second up. Here's the ball. 6 meters per second up, 5 meters per second horizontally. What is the horizontal component of its velocity at the highest point? So first of all, let's draw this image. So we've got a ball. Beep, and it's going to come down. And this is the highest point. At the highest point, the horizontal component is going to be equal to the horizontal component anywhere during the flight, because the horizontal component doesn't change because it's constant. So it's going to equal 5. It's a trick question. 5 meters per second. B. What is the vertical component of the velocity? No, that's going to change. At the highest point, we should always remember at the highest point, the vertical component of the velocity is 0. 0. And the way I remember this is I think about like throwing an object up in the air, because that's also vertical, that's projectile motion. Look, if you slow down the video, you can see that the object stops and then comes down. So it's 0 at the highest point in the vertical component. Next question. A crow, غراب, is flying horizontally with a constant speed of 2.7 meters per second. 2.7 meters per second. When it releases a clam, this is a clam. Okay. So obviously crows are very, very clever, and to break the clam, they drop it from a height to break it and eat the inside. So it releases the clam from its beak, as shown in figure 4.38. The clam lands on the rocky beach 2.10 seconds later. So after 2 seconds approximately, the clam lands on the rocky beach. Just before the clam lands, what is the horizontal component of velocity? So we should all know by now that the horizontal component of velocity doesn't change, so it's going to be 2.7 meters per second. So over here, it was traveling 2.7 meters per second. Over here, it's traveling 2.7 meters per second in the horizontal component. Why? Because we are ignoring a resistance. What is the vertical component? What is the vertical component? That is different. So what is the vertical component of velocity? Let's have a look. So basically, in order to work this out, we need to do this. So we need to consider gravitational acceleration, or acceleration towards gravity. And so we are working out VYF, the final velocity, and that equals the initial velocity. Now, lucky for us, it was released, as you can see here, released, which means from 0. So the initial velocity is 0 minus GT, minus 9.81 times T, which is 2.1, because the formula is actually over here. The formula is Y, VYF is how we VYI minus G times T. That is the formula. Okay, and so that's what we have over here, which is approximately 20 meters per second, which is significant enough to break the clam. You know, it'll produce a force that's big enough to break the clam. Why? Because the kinetic energy is half mv squared. So the higher the velocity, the more kinetic energy it will have. So 20 meters per second squared is 400 meters per second multiplied by the mass, whatever the mass of the clam is. It's going to give you a big amount of energy, enough to break the clam. Anyway, that is the speed in the vertical axis. What is the distance traveled in the x direction? So once again, we have the formula. We can use the formula. So the formula is going to be x final يساوي x initial, x initial plus vxit. X initial is 0. What's the initial velocity in the x-axis? That's 2.7. 0 times t, which is 2.10. Really what we're saying is that distance equals velocity times time. Velocity equals distance over time. And so distance is equal velocity times time. So that's what we're saying. And that is going to be equal to approximately 5.5. Let's have a look. 2.7 times 2.1, and that is 5.67. 0.67 meters. That is the final distance. What is the clam's final velocity? Now that is slightly different. Now we know the final velocity in the y component is 20.6 meters per second. We also know the final velocity in the x component is the same as the initial velocity, which is 2.7. So now we have a triangle. The triangle looks like this: 2.70 meters this way, and we have minus 20.6 this way. We are trying to work out velocity here. So it's going to be 2.7 squared plus 20.6 squared. No, I didn't even bother with the negative because, well, it doesn't matter. So it's going to be the square root of this, of course. So it's going to be the square root of 2.7 squared plus 20.6 squared. And you know, when you square the negative, it gets rid of it anyway. So it's going to be 20.8 meters per second. Okay. And finally, a bonus point which says at what angle did the clam hit the water? So we are trying to work out this angle here, I suppose. Once again, 20.6 divided by 2.7, and that is opposite over adjacent. Shift 10, answer 82 degrees. So the angle is 82 degrees, 82.5 degrees past the x, or past the horizontal, or below the horizontal. So that's the horizontal. It's going to be 82.5 degrees below the horizontal. Excellent. And that's how you solve that one. Okay, very good. Let's go to the next one. Ah, we finished. Lesson check. Alhamdulillah. Identify which of the following shapes seen in the path of a projectile: straight line, parabola, ellipse, or hyperbola. Hyperbola? No, parabola. 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 It always looks like parabola. 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 Okay. There's an exception, which is like if you launch an object straight up, or if you release it, then it's like a straight line because there is no x component. But we still consider it parabola. Okay. Except for that exception. So that's 43, parabola. Okay. 44. How must a projectile be launched in order to maximize its angle? Launch it at 45 degrees. Okay, 45. Jennifer's bowling ball is dropped from rest. Okay, dropped from rest. That's Jennifer. And then Jeanette's bowling ball is thrown horizontally at the same time. And that's Jeanette's bowling ball. And it is thrown horizontally at the same time. And then it says, after the balls are released, is the acceleration of Jennifer's bowling ball greater than, less than, or equal to the acceleration of Jeanette's bowling ball? Explain. Well, we already know that projectile motion deals with objects that are released. So at the moment of launch, that is not projectile motion. At the moment the ball is kicked, it's not projectile motion. At the moment the missile is launched, the bullet is fired, that is not projectile motion. The moment after, when it's released on its own, no acceleration is experienced in the horizontal axis. And we're talking about the projectile motion here. We're talking about the moment after it was released. So when they are released, what's going to happen? They are both going to experience the same acceleration downwards. There's no acceleration in the x direction, no acceleration. Only acceleration is in the y direction, which is g. So that's going to experience g. And this ball here is going to experience g as well. And they're both exactly the same, 9.81 meters per second acting downwards. So they're going to be the same. 46. Three projectiles, A, B, and C, are launched with the same initial speed, but with different launching angles. Rank the projectiles in in order of increasing horizontal component of initial velocity and time of flight. Okay. Horizontal component. So remember velocity, this is v, has a horizontal component, vx, and a vertical component, vy. They want us to arrange it in order of increasing horizontal component. So we start with the smallest horizontal component, and then we go to the largest horizontal component. And so A has the smallest horizontal component. And if it was launched directly upwards, it wouldn't have a horizontal component, aslan. So A has a smallest horizontal component, B is bigger, and then C is the biggest. So for that one, it's just A, B, C. Okay? A, B, C. A is, yeah. Next, A is smaller than B, which is smaller than C. B is asking for time of flight. The time of flight. So which one has the biggest, which one experiences the largest time in flight, or the biggest time in flight, or the longest time in flight? And the answer for that is A. Okay, if you launch an object directly upwards, it's going to experience the longest time in flight, but it's going to have the smallest range. So in this case, A is going to experience the longest time of flight. But remember, the question's asking for in order of increasing. So we start with the smallest and then we go to the biggest. So C is going to experience the shortest time of flight, then B, then A is going to experience the longest time of flight. Okay, next. Calculate what is the maximum range of the golf ball. An example 4.12. 4.12. Okay, now we know that range is going to equal r, which is the initial velocity squared over something over g. Okay, so let's have a look. 47. Okay, so we know it's the, let's have a look at question 47, Aslan, the formula, the equation. That's the golf question. 13.5 for the initial velocity, and angle of 54. Maximum range. So maximum range is going to equal R max Yisawi, the initial velocity squared over G, which we know is going to be 13.5 squared over 9.81, which is equal to 18.6 meters. So that's not very long, but that is expected. So 18.6 meters over here. That is the maximum range, which we will achieve at 45 degrees. Okay. Okay, next, 48. I think I will do this as the last question, and then I will let you do questions 49 and 50 on your own. And if you need to check those, you can come and see me. A snowball is thrown with an initial velocity of 7.5 meters in the x direction and an initial y velocity of 8.2. How much time is required for the snowball to reach its highest point? And of course, it gives you one big hint. At the highest point, the y velocity is 0. So we just need to work out when will VYF equal 0. That's what we need to work out. When will VYF equal 0? So let's have a look. So we have initial velocity is very good. So for this question, it doesn't even give us an angle, does it? Nope, there's no angle. So it's going to be even easier than I thought. VYF is how we VYI minus GT. So the initial velocity in the y direction was 8.2 minus 9.81 multiplied by t, and we know that that's going to be 0 because at the highest point it tells us that vyf is going to be 0, and that's going to be, let's rearrange this. I'm going to get rid of this, minus 8.2, so that gets rid of that. And then we have minus 8.2 on this side, Yisawi, negative 9.81 times t, so I'm just going to divide by negative 9.81, so that gets rid of that as well, and that equals t. So t is going to equal to minus 8.2 divided by minus 9.81, which is 0.84 seconds. Okay, gentlemen, well, I think I'll stop there. That is projectile motion. It's not tricky. It just needs you to understand the question. And as you saw before, even I made a mistake with the question because I was thinking I was doing velocity instead of position. So just make sure that you read the question carefully. And if you have any questions, I am free and available, even on Thursday. Please come and ask me any questions, or in Teams, or during breaks and duties and such. Okay, all the best. Adios, over and out.